Hello friends, this is Nishant Daniel and I'm currently studying in Avi College of Engineering, Bangalore. So today I'm going to present to you my chemistry assignment, which is a self-study assignment, a Chitin Nanofiber transparent paper for flexible green electronics. So, what is a flexible electronic? Flexible electronics, also known as flex circuits, is a technology for assembling electronic circuits by mounting electronic devices on flexible plastic substrates such as polyamide, PEEK, or transparent conductive polyester film. Additionally, a flex circuit can be screen printed silver circuits on polyester. There are many advantages to it. It's flexible, it's light and thin, it's unbreakable, and it's having cost advantages, and it has constant innovation all the time. So, before I discuss about the Chitin nanofiber technology, I'm going to give you a hint about the idea of green electronics. The idea for green electronics in part refers to the materials used in the production of computers, cell phones, televisions, and dozens of other electric devices. While it may be cheaper to use more toxic materials when building devices, electronic manufacturers are being urged to invest in eco-friendlier materials. So what are the advantages to green technology? One of the most obvious benefits to building with green technology is environmental impact. Green technology helps reduce emission, conserves water, reduce waste, and consume less energy than conventional technologies. Green building also use materials more efficiently. So, what are chitin nanofibers? Chitin nanofibers, as in CHNFs, are mainly extracted from crab and prawn shells and recently found in small amounts in edible species of mushrooms. CHNFs are composed of chitin compound. Chitin in powder form is obtained from fish industry waste, which is otherwise thrown as industrial waste. Since CHNFs are biodegradable, having typical width 10 to 20 nanometers and large surface to mass ratio, thus they are being prepared, studied, and applied more recently worldwide, along with rapidly growing nanotechnology dealing with better properties of materials when the sizes are being in the range of 1 to 100 nanometer. Fibrillated chitin in the form of highly viscous gel suspension in water has found scope in pharmaceuticals, chiral separation, fillers in silsexquoxane. When blended with inorganic metals to prepare advanced hybrid organic inorganic composites, they have applications in electronics, electrical, optical devices, and much needed solar energy productions. After this, we are going to talk about the highly transparent chitin nanofiber paper, which is used in today's technology. Chitin nanofiber or gelatin nanocomposite is synthesized by immersion method, followed by drying at room temperature. The CHNF content in the CHNF is controlled in a broad range by changing the concentration of gelatin solution from 2 to 5 to 10% during the immersion process. The prepared CHNF shows uniformly nanofiber network structures which embedded inside the gelatin matrix. SSQUA copolymer CHNFs, transparent composite sheets or thin film is prepared which has optical, thermal, and mechanical properties. Prepared sheet was highly transparent due to the nano-sized effect of nanofibers, as the size of fibers was 1/10 of the wavelength of light that made materials free from scattering. Therefore, the sheet was transparent. Therefore, with the highly transparent and improved mechanical properties, the prepared CHNF gelatin nanocomposite films may offer promising and broad prospects in the field of good packaging and biomedical industries. So, what are the uses of CHNF in flexible green electronics? The transparent paper made of chitin nanofiber is introduced, and its utilization as a substrate for flexible organic light emitted diodes. Given its promising microscopic properties, biofriendly characteristics, and availability of raw materials, the utilization of CHNF transparent paper as a structural platform for flexible green electronics is envisaged. So, now I'm going to give you some examples of flexible green electronics which are derived from chitin nanofibers. So the first one is squid pen. Squid pen derived chitin is second most abundant biopolymer on earth after cellulose. Because of the promising macroscopic properties of the CHNF transparent paper, the bio-friendly characteristics, and the availability of raw materials, its utilization as a structural platform for flexible green electronics is anticipated. The second example for the derivative of CHNF is flexible organic light emitting diodes or LEDs. The fabricated flexible OLED device on the CHNF paper to demonstrate its potential as a biodegradable substrate for flexible green electronics. And OLED with the device structure shown in the figure is fabricated on a 40 micrometer thick CHNF paper that is spin coated with thin polymethyl macrylate PMMA layer as a surface planarization layer. A reference device is fabricated using a 50 micrometer thick pen substrate film. It shows the digital images of the OLED fabricated on the CHNF paper operating stably in both flat and flexed surfaces. The third example for this is wearable electronics example sensors that operates as being attached to the skin. Given its promising attributes such as biocompatibility, biodegradability, transparency, flexibility, and printability, our CHNF paper may also serve as structural platform for wearable electronics, example sensors, that operates as being attached to the skin. Figure shows a CHNF paper attached on skin that deforms conformally along with the skin. CHNF paper itself is not sticky and thus sprayable bandage is used as an adhesive. So, in conclusion, I want to say that the preparation of CHNF's transparent composite sheets or thin film showed optical, thermal and mechanical properties which complemented their use in modern technology is envisaged. The properties improved on blending CNFs with the copolymer to larger extent has increased the scope of CNFs to even broader areas of electronics. Thank you.